and welcome to another episode of Beyond the Syllabus. In today's episode, we will be looking into the galvanic cell and a Duracell battery. Ever wondered what goes on in these little things? Well, it's pretty cool, so I'll walk you through that and also look at the similarities and differences between the two. We will also discuss the features listed before. First, we will look at metal activity. Metal activity is a way to put all the metals in a series that determines how reactive they are. This is important for the type of chemistry in galvanic cells and Duracell batteries, especially redox reactions. This is a simplified reactivity series of metals table. We can see that the most reactive metals start at the top and then decrease if you go down the list. It is also used to determine the ease of oxidation. If we look into the metal activity in the galvanic cell, the two metals are zinc and copper. The table says that zinc is more reactive than copper, and this is correct, because it's the zinc that's oxidizing. An easy way to determine which metal oxidizes, if you didn't have the series table, would be on a periodic table, because the metal activity increases from right to left and from up to down. In the dry cell battery, the zinc is more reactive, which makes it oxidize. That leaves the manganese, which is less reactive. The graphite is an inert electrode that conducts a charge and acts as a passageway. Now to explain the galvanic cell, with the help of Luigi Galvani. In a galvanic cell, zinc has a tendency to give away electrons and copper wants to gain them. So zinc undergoes oxidation and loses electrons. The electrons travel through the external circuit, which is another word for the wire. The half equation for the oxidation is below. Zinc goes to a zinc ion and 2 electrons. The 2 electrons go through the wire and the zinc ion goes back into the solution. However, now there is an imbalance in charges. This is where 2 chloride ions come down from the salt bridge to balance out the charge. If we look over to the copper now, once the electrons reach the copper electrode, 2 electrons travel down to where the copper comes in contact with the copper sulfate solution. Now, a copper ion takes the electrons and becomes a copper atom. The half equation for this is below. The reduction equation is a copper ion combining with 2 electrons to form copper. Now a similar problem arises in this side of the cell like the other. There is an imbalance now because the copper ion has turned into an atom. To combat this, 2 potassium ions come from the salt bridge to balance out the lost copper ion and balance the charge. Alright, now we have the reduction half equation and the oxidation half equation that we worked out from before. The next step is to put them both together in one redox reaction. Red for reduction and ox for oxidation, redox. Once we have the equations, we see that there are 2 electrons on each side. So now we can cancel those and it leaves zinc and a copper ion to copper and a zinc ion. Now to work out how many volts are produced, or the reduction potential. We know that copper has a reduction potential of 0.34. The zinc reduction potential changes because the zinc is oxidizing in this cell, so we flip the sign. Now we add the 2 reduction potentials together and we get an overall voltage of 1.1 volts. The 1.1 volts is known as the standard cell potential. This is what the whole cell produces. There are 2 types of reduction potentials, theorized and measured. Theorized is calculated by using the table of standard reduction potentials. This is universally known and used when calculating it in theory. Measured reduction potential is what is actually produced in a prac or in real life. This usually decreases because of a number of factors like resistance, oxidation on electrode, temperature, concentration of solutions, and gas pressure. The standard temperature is supposed to be 25 degrees. So, if that's not the temperature when doing the experiment, the reduction potential can change. The problem with galvanic cells is that eventually the metal that's oxidizing will run out, because bit by bit every oxidation reaction loses part of the zinc. Very slowly, of course, but it's a finite resource for electrical energy. The copper doesn't run out because it actually increases because it's reducing. To determine whether the redox reaction is spontaneous or not, it's quite simple. If the redox reaction cell potential is positive, then the reaction will proceed in the forward direction, making it spontaneous. If the reaction is negative, then it will not move forwards, making it non-spontaneous. All non-spontaneous reactions cannot be used to produce energy. If both half cells add up to be negative, then no energy will be produced. The purpose of a galvanic cell is to produce electrical energy. Having electron flow, which is known as the current, means you can power a light or radios or watches, etc. Now that we've learnt all this, we will now compare it to a dry cell battery. The dry cell battery, very recognizable, but the inside's not so much. We have a steel base and a steel cap. The inside of the battery consists of a zinc chamber, which holds the electrolyte paste and a graphite rod. There are two terminals, one positive and one negative. This is a more simplified version of the inside of the cell. The cathode is the graphite rod, and the anode is the zinc casing. The zinc oxidizes and sends electrons to do some work, whether that be a TV remote or a light. Then they are regained by the graphite rod, and then the ions in the electrolyte pick up the electrons and reduction occurs. The reduction reaction. Manganese 4 oxide combines with an electron and reduces to manganese 3 oxide. The equation to that sequence is below. However, the proper reduction reaction equation is this. The oxidation reaction is less complex. It is below. Now the zinc atom goes to zinc ion and 2 electrons. Those electrons flow through the wire, which is known as the current. The current is the rate at which the electrons flow through the wire. This then starts the cycle again, when the electron reaches the graphite rod. Now we have the oxidation and reduction half equations. The next step is to put them both together in a big equation. We now see that there are 2 electrons on each side, so we can cancel them. Then we are left with one fully balanced equation. The standard cell potential of this battery is 1.5 volts. Now, just like the galvanic cell, the dry cell battery has a finite supply of metal, and once all the zinc has oxidized, the battery runs out and dies, and you won't be able to change the channel on your TV. In some batteries, the components can be acidic and toxic. However, with the dry cell battery, the components are weakly acidic and non-toxic, and there are few environmental consequences on disposal, which is great. The dry cell battery is very cheap, and it's used for so many things, like your alarm clock, your TV remote, your remote control car, just to name a few. Alright, now that we have gone through both the battery and cell, we can now compare the two in depth. The chemistry of both batteries have redox reactions. However, the dry cell battery's chemistry is a bit more complex, with the reduction equation featuring ammonium to ammonia and water. The water contributes to the conductivity of the paste, and the ammonia complexes with the zinc ion to form a stable complex ion in the paste. Both batteries have spectator ions. Sulfate is the galvanic cells, and chloride is the dry cells. The construction of the batteries are different. The dry cell battery is much more practical for daily uses. The galvanic cell is mostly used for learning purposes, because you can see what's happening. Rather, the dry cell battery is covered. The uses can be similar and different. In theory, you can use a galvanic cell to power all the things that a dry cell does, but it's not practical. Having your beakers on a coffee table hooked up to your remote is quite annoying. So mostly the uses for galvanic cells is for learning purposes, which is usually connected to a light bulb or an LED. The dry cell is used to power commercial things like these. The limitations are the same for both. They are finite resources for energy. They will run out eventually. The limitations for a galvanic cell can also be that it's not practical, so the uses is limited to maybe a light bulb or an LED. Much of the galvanic cell is a risk to come in contact with both skin and eyes, so you would have to be careful around it. In regards to metal activity, the zinc is the metal that is most reactive. This is similar in both. However, the other metal is not similar, which produces different voltages. Talking about voltage, the galvanic cell's voltage is 1.1 volts, and the dry cell's is 1.5 volts. The current is higher in the dry cell to the galvanic cell. The transfer of electrons is the same. They both have the same structure, as in the electrons go into the wire and enter the cell, and then are transferred via ions to repeat this process. They both have 2 metals and an electrolyte to make this possible. The flow of electrons is due to redox reactions.
The redox reaction in both are different from one another because there are different materials being used. The anode is zinc in both, whereas the cathode is different. But both batteries have cathodes and anodes. The two have the same reduction potential for oxidation, but different reduction potential for reduction. The measured and theorized values are different in both batteries because of potentially the wires or how old the battery is. The galvanic cells has half cells and the dry cell doesn't. Both systems will change over time because they will lose one of their metals and gain in the other. This will decrease the productivity of the battery/cell. And to finish, they are both spontaneous reactions because they have positive reduction potentials, meaning the electrons will flow and the battery cell will work.
That concludes our video. Hopefully you've learned a bit about the galvanic cell and a dry cell battery. From all of us here at Beyond the Syllabus, we thank you for watching. That was terrible. It's too hard to explain on the camera, so no. The transfer of electrons in the battery is a series that determines. Okay. Okay. Oh Jesus, that was a bit hard. Oh my God, Jock, come closer. Oh, do it. This is just weird. Discuss the listed. I look like an idiot. Learned not a half cell. Yes!